In this section, we're talking more about determinants. And since we know about transpose, let's talk about the determinant of a transpose. The determinant of A transpose is equal to the determinant of A. All right, so when finding the determinants, we automatically have to assume that A is a square matrix. Otherwise, you can't find a determinant. But let's take a look at this matrix A, and what we want to do is find the determinant of A. This is nothing more than 12 plus 35, which is 47. While we're here, let's do some review. Because we got a number, that means that there exists an A inverse, which means A is an invertible matrix, which means it's a non-singular matrix. Since A has a determinant that is not 0, it has an inverse. Therefore, that makes it non-singular. There is more than an A matrix that we can form. So that was a nice review. But that's not what they asked us. Let's talk about A transpose. A transpose is nothing more than the rows change into columns or the columns change into rows, however you want to say it. The determinant of A transpose is 47. Let's take a look at matrix B. Matrix B is 2, 4, 3, 6. The determinant of B is 12 minus 12, which is 0. Which means there does not exist a B inverse. This is all review. Which means B is not invertible. Which means B is a singular matrix. Let's look at B transpose. Again, the rows change into columns or the columns change into rows. Finding the determinant of B transpose, we get 0. The next property we're going to talk about is the determinant of an inverse function. The determinant of A inverse is equal to 1 over the determinant of A, and vice versa. The determinant of A is equal to 1 over the determinant of A inverse. So one more time, this is the only one that I showed on the handout, but understand the other way is true as well. The determinant of A is equal to 1 over the determinant of A inverse. Let's do an example. Here is matrix A, negative 5, 2, 4, negative 3. The determinant of A is equal to 7. And if I just wanted to find out what 1 over the determinant of A is, it is nothing more than a number, 1 over 7. Remember, the determinant of A is a number. I'm not dividing by a matrix, I am just dividing by a number. So 1 over the determinant of A gives me 1 over 7. The next thing that we're going to do is find A inverse. And as usual, I'm going to set A equal to the identity matrix and row reduce until I get the identity matrix equals A inverse. This is A inverse. Now that we have the A inverse, let's find the determinant of A inverse. There are fractions, but that's okay. And you see that the determinant of A inverse is 1 over 7. The determinant of A was 7. The determinant of A inverse was 1 over 7. 1 over the determinant of A equals 1 over 7, which is the determinant of A inverse. 1 over the determinant of A inverse is the same as the determinant of A. It's a cool little trick. Now, the reason I showed you the inverse is because there is a shortcut to finding the inverse matrix of a 2 by 2. First thing that we need to know, A must be a square n by n matrix, and 2, the determinant cannot equal 0. The old way of finding a 2 by 2 A inverse was the setup A equals I, row reduce it till you get I, and you get A inverse on this side. Let's show you the new way, the shortcut. Here's the new way for finding the 2 by 2 A inverse matrix. matrix A will be given. A inverse is equal to 1 over the determinant of A, and all you do is you have your diagonals switch place and you put negatives on the opposite diagonals. So A sub 1, 1 and A sub 2, 2 will switch places, and whatever signs you had here will flip to the opposite sign. Also remember, if the determinant of A equals 0, then there does not exist A inverse. Let's do an example. Matrix A is 7, 4, 3, 2. To find A inverse, the first thing I need to do is find the determinant of A. The determinant of A is 2. To find A inverse, you take 1 over the determinant of A, switch the A sub 1, 1 and the A sub 2, 2 around, so now it's 2 and 7 instead of 7 and 2 on the diagonals. Your other diagonal elements will just change sign. Multiply through, and there's your A inverse for a 2 by 2. Shortcut now available. You can always double check and make sure that your A inverse is right by doing it the long way, method 1, setting A equal to the identity and working it out Gauss-Jordan-wise until you get the identity in A inverse. And notice, after reducing, I get the same thing. It's a nice trick to have. Here is another property of determinants. The determinant of matrix A times the determinant of matrix B equals the determinant of the matrices A times B. It may seem a little confusing in the beginning as far as what this is saying, but here we go. We have matrix A and we have matrix B. The determinant of A is negative 11 and the determinant of B is negative 9. Individually, those are the determinants for A and B. The idea behind this property is multiply A times B. When we do, we get 5, 11, negative 4, 11. The determinant of A times B is 99. The determinant of A all by itself was negative 11. The determinant of B all by itself was negative 9. When we multiplied A times B together, we notice the determinant of A times B is equal to the two determinants multiplied together. It's very true. Another property of determinants is when you have the determinant of K times A. This will end up giving you K to the N because it depends upon what R space we're in that we're talking about for the size of the matrix, times the determinant of A. So for example, I have K times A sub 1, 1, K times A sub 1, 2, K times A sub 2, 1, K times A sub 2, 2. As we know from the previous section, I can factor out a constant from a row and place it outside the matrix. We took out a K from row 1 and a K from row 2. If it is the exact same constant, hence we get K squared. Please understand that in 3.2, we only took a constant out of a row. Now, these constants can be different, but this property is talking about when the constant that we're factoring out from each row is exactly the same. Here we have an example of matrix A, and we can see the determinant of A is 8. In chapter 2, I would ask you to find something like 5 times matrix A. And this resulting matrix I'll call B, and the determinant of B is now 200. Let's take this problem and go backwards. Here is matrix B. I'm going to use this property of factoring out a constant from each row, and it turns out to be the same constant. I took out a 5 from row 1 and a 5 from row 2. 5 times 5 is 5 squared. This looks like our property. The determinant of B is whatever you pulled out, in this case the 5 squared, times the determinant of your matrix. And it so happens to be 200. So when I take out a constant from a matrix, it affects the determinant. Whatever you factor out of the matrix can be different from each row, but again, this property is only when you take out a constant that is the same from the entire matrix. In this case, this is a 2 by 2, so I have a power of 2. If this was a 3 by 3 and each row had a 5 that I could factor out, this would be 5 cubed. So this outside number that you factored out affects the determinant of that matrix.